Today, we're tackling a big one, maybe the big one.
You see it everywhere, right?
Yeah.
T-shirts, mugs. But what's actually going on inside that equation?
It really does hold some deep secrets about how the universe works, and the observation you sent over, that's a perfect way in.
Yeah, it really struck me. Looking at the numbers, you take just 1 joule of energy, right? One single unit.
Mm-hmm.
And the m, the mass equivalent, it's just incredibly tiny, like 1.1 times 10 to the minus 17 kilograms. Vanishingly small.
Almost nothing.
But then the other side, c², the speed of light squared. That number is colossal. About 9 times 10 to the 16th.
It's huge. Absolutely huge.
So you've got this tiny mass multiplied by this giant number to get. 1. Feels, I don't know, almost like a paradox. A 34 order of magnitude gap.
It does seem strange, doesn't it? But that massive difference in scale, that apparent paradox, it's not a mistake. It's actually pointing towards something really fundamental about mass and energy.
Okay, so that's our mission for this deep dive then. Let's unpack that. Let's figure out why those numbers are the way they are.
Exactly. And the answer lies in a few places. Partly in how we define things, our units, partly in what C really represents.
And partly in understanding mass itself as this incredibly concentrated form of energy.
Right. So maybe the best place to start is with the E. With energy, how do we even define a joule?
Okay, yeah. The standard unit. What is a joule, fundamentally?
Well, formally, it's the energy used when you apply 1 Newton of force over 1 meter.
A Newton, that's force,
Right,
which involves mass and acceleration.
Precisely. A Newton is the force needed to make 1 kilogram accelerate at 1 meter per second squared. So 1 kilogram times ms².
Okay, so 1 Newton over 1 meter, that means 1 joule is 1 kilogram times meter per second squared times another meter.
You got it. 1 joule breaks down completely to 1 kilogram times meter squared per second squared. So kg-ness.
Ah, look at that. Kilograms, meter squared, second squared. It's already got mass and, well, velocity squared baked right into its definition.
Exactly. So if energy joules is equivalent to mass, kilograms, the equation needs a conversion factor with units of velocity squared, like mc², just to make the dimensions work out. It's almost required by how we set up our measurements.
That's really interesting. So the c² isn't just plucked out of thin air. It's dimensionally necessary because of the joule itself.
Right. And then you've got the m, mass. Usually we think inertia, resistance to acceleration.
The kilogram, our standard lump of stuff.
But Einstein gave it a twist. He said mass isn't just inertia. It's a form of, well, congealed energy, as you put it. It's energy packed incredibly tightly.
We'll come back to that, I'm sure.
Yeah.
But okay, E and M, now the big one. C, the speed of light. C. Everyone knows it's fast. 299,792,458 meters per second precisely. In fact, the meter is now defined based on C. But it's more than just how fast light travels, isn't it?
Oh, much more. It's the universe's ultimate speed limit. Nothing, not information, not energy, not any cause and effect can travel faster than C.
Okay, the cosmic speed limit.
But even deeper than that, C is really a fundamental constant that links space and time. Think about it. Meters per second. It connects distance and duration. It's the conversion factor that tells you how much space is equivalent to how much time in the fabric of space-time.
Wow. Okay. So it's not just a speed. It's like the structural constant of space-time itself.
That's a great way to put it. It relates how we measure space to how we measure time, which is why it pops up in an equation linking mass, which exists in space, and energy, which unfolds over time.
Okay, this is starting to connect. The joule demands a velocity squared term for dimensional reasons. C is the fundamental space-time velocity constant. So c² naturally slots in there.
Exactly. Now, back to that huge number you started with, c², roughly 9 times 10 to the 16th c stat. That's the multiplier.
That's the reason a tiny gives a huge E.
Right. It
Yeah.
scales it up massive. Think about a penny, just a normal copper penny.
Okay, weighs a few grams.
If you could somehow convert all that mass, every single atom, directly into energy, according to mc²,
How much energy are we talking?
you'd release something like 18 kilotons of TNT equivalent. That's roughly a Hiroshima-sized explosion.
And 1 penny.
Yep. Enough energy to power a major city like New York for, I think it's at least a couple of years.
That's genuinely mind-boggling. Just sitting there in your pocket, all that potential.
It really highlights how much energy is locked up in even tiny amounts of matter.
So why? Why is c² such an astronomically large number when we measure it in our everyday units, meters and seconds? Is the universe just built that way?
Well, yes and no. This is where we get to the heart of your original question. The resolution to that Paradox, that enormous number. It's mostly our fault.
Our fault.
It's an artifact of the units we chose. The meter, the kilogram, the second. They're human-sized, convenient for us for building things, for measuring our days.
Right, they weren't handed down from on high based on cosmic principles.
Exactly. They're arbitrary from the universe's point of view. Theoretical physicists often get around this using something called natural units.
Natural units, what's that?
It's where you define your units based on fundamental constants of nature. For instance, you could set the speed of light, c, to just be 1.
Set c equal to 1. How does that work?
Well, imagine you define your unit of speed as light years per year, or maybe light seconds per second. In that system, the speed of light is just 1, no huge number.
Okay, so if c1, the EMC salts just becomes
PEM
equals m. Whoa.
In a system of natural units where c is 1, mass and energy aren't just equivalent, they are literally the same thing. Measured in the same units, the distinction just dissolves.
So that whole 34 order of magnitude gap,
Yeah.
the tiny m and the huge c squared,
Yeah.
it just vanishes. It's all because our meters and seconds make c look big.
Precisely. The fundamental physical law is simply EM. Mass is energy. Energy has mass. The c squared is just the, let's say, awkward conversion factor we need, because our everyday units of mass, kilograms, and energy, joules, which involve meters and seconds, aren't naturally compatible. They measure the same fundamental stuff using wildly different human scales.
That's the aha moment. So my initial baffling observation wasn't a deep cosmic mystery, but a reflection of our own measuring sticks being, well, a bit clumsy on a cosmic scale.
It perfectly highlights how our perspective, our measurement system, can sometimes obscure really profound and simple underlying reality.
Okay, so c squared is the conversion factor. But why light speed specifically? If mass converts to energy, why does light get the starring role?
Good question. It's because when you do convert mass into pure, unbound energy, think matter-antimatter annihilation, the most complete conversion possible, what form does that energy take?
Light or radiation.
Oh, exactly. Electromagnetic radiation, gamma rays, X-rays, maybe light. And all electromagnetic radiation travels at c in a vacuum. So c is the natural speed associated with energy when it's been liberated from mass. It connects the energy stored in mass at rest to the speed that energy moves at when released.
Right. And the squared part, EMC squared, y squared. You mentioned kinetic energy earlier, KE of ESC, alpha 7 phi. Is it related?
It's definitely related conceptually. In physics, energy often involves squared terms related to motion or potential. mc² is specifically about the rest energy.
Rest energy.
Yeah, the energy an object has simply by existing, just by having mass. Even if it's perfectly still, it's an intrinsic baseline energy content.
So it's not the total energy if the object is moving.
Correct. The full relativistic equation is a bit more complex. It's EF mono plus PC, where P is momentum.
Oh, okay.
But you see, if the object is at rest, momentum P is 0. So the PC term vanishes, and you're left with EMCO, take the square root, and ESMAM4 too.
So the squared term comes from the deeper relativistic relationship between energy, mass, and momentum in four-dimensional spacetime.
That's right. It falls out naturally from the geometry of spacetime. It ensures that the rest energy is correctly defined as this fundamental property linked to mass.
Simple equation, profound geometry. Okay, so let's see this in action. Where does this conversion actually happen? You mentioned nuclear physics.
Absolutely. The mass defect is key here. Take an atomic nucleus, like helium. It's made of protons and neutrons.
Right.
If you weigh the helium nucleus, and then you weigh the individual protons and neutrons separately and add up their masses, you find something strange.
They don't match.
The whole nucleus weighs slightly less than the sum of its puds.
Where did the mass go?
It was converted into energy. Specifically, the binding energy that holds the nucleus together, that missing mass, delta mu, is released as energy according to ECE.
That's incredible. So the very stability of atoms relies on this mass-energy conversion.
It does, and it's the principle behind nuclear power. In fission, you split a heavy nucleus, like uranium-235. The pieces you get, the fission fragments, plus any neutrons released. Their total mass is slightly less than the original uranium nucleus.
And that tiny mass difference times c squared
equals a huge energy release. Fissioning 1 kilogram of U-235 releases about 82 terajoules. That's 82 million joules.
Wow. And what percentage of the mass is actually converted?
It's actually quite small. Only about 0.09% of the uranium's mass turns into energy. But because c squared is so enormous, even that tiny fraction yields immense power.
And fusion. like in the sun.
Fusion is even more efficient, in a way. You take light nuclei, like hydrogen isotopes, and smash them together to make heavier ones, like helium.
Which also weighs less than the starting ingredients.
Yes. In the main fusion process in the sun, about 10.7% of the mass of the hydrogen that fuses is converted directly into energy.
0.7%. That's almost 10 times more efficient than fission, percentage-wise.
It is. And the sun does this on an unbelievable scale. To produce the sunlight and heat we feel, the sun converts over 4 million metric tons of its own mass into pure energy every single second.
4 million tons.
Per second. 4.26 billion kilograms. Gone, turned into energy every second. That's what powers the solar system.
Okay, that just puts everything into perspective. The sheer power locked in matter.
But even fusion isn't the ultimate conversion.
Right, you mentioned matter-antimatter.
Annihilation, that's the perfect 100% conversion. Mass goes in, pure energy comes out, no leftover bits.
And this works both ways. Can energy turn into mass too?
Absolutely. It's called pair production. If you have a high-energy photon, like a powerful gamma ray, and it passes close to an atomic nucleus, it can spontaneously transform its energy into a particle and its corresponding antiparticle, for instance, an electron and a positron.
So E turns into M.
Exactly. The photon's energy has to be at least equal to the combined rest mass energy of the pair it creates, again, precisely according to mc². This must have happened constantly in the very early universe when it was just a soup of energy.
The origin of matter itself.
Largely, yes. And the reverse process, annihilation, is when that electron meets that positron.
Poof.
Poof is a good word for it. Their entire mass is converted back into energy, usually a couple of high-energy photons, gamma rays, shooting up in opposite directions. Total conversion.
So let's just quickly compare the energy bang for your buck. Chemical reactions, like burning fuel.
Tiny mass conversion, almost zero, something like what, 10 to the minus 9%? Negligible mass change.
Nuclear fission.
Around 0.1% mass conversion, millions of times more energy release than chemical.
Nuclear fusion.
Better still, up to about 0.7% mass conversion. Power stars.
And matter-antimatter annihilation?
100% mass conversion, the absolute maximum possible. Thousands of times more energy released per unit mass than even fission.
That really lays it bare. Mass is the ultimate concentrated energy source.
It truly is. And understanding this didn't just impact energy calculations, it fundamentally changed how we view physical law.
How so?
Before Einstein, we had two separate bedrock laws: conservation of mass and conservation of energy. Matter couldn't be created or destroyed. Energy couldn't be created or destroyed.
Right, taught in basic chemistry and physics.
mc² merged them. It showed mass and energy are interchangeable. So now we have one more profound law: the conservation of mass energy. The total amount of mass energy in a closed system is constant.
We can just change form from mass to energy and back again.
Precisely. And this has huge implications even for gravity.
You mentioned general relativity earlier.
Right. Einstein's theory of gravity says that what curves space-time, what creates gravity, isn't just mass. It's the total energy and momentum density
So because mass is a form of energy,
that contributes to gravity. But so does all energy: kinetic energy, thermal energy, even the energy stored in gravitational or electromagnetic fields themselves. They all add to the gravitational charge, so to speak.
so technically a hotter object, because it has more thermal energy, has slightly more mass.
Infinitesimally more, yes. And it exerts infinitesimally more gravity. Same for an object that's moving. Its kinetic energy adds to its relativistic mass.
That's wild. Our everyday intuition about mass being static is just wrong at a fundamental level.
It's a low-energy, low-speed approximation. Reality is more dynamic. Mass is energy waiting to happen, and energy has mass.
And cosmologically, you said it explains the origin of matter from the Big Bang's energy.
Yes, through pair production as the universe cooled, E converting to M. It's central to that whole story, and it's still relevant in modern cosmology, thinking about things like dark energy, which is essentially the energy of empty space itself.
Which must have an equivalent mass, and therefore gravitational effects.
Exactly. And even exotic ideas like Hawking radiation, where black holes are thought to evaporate by creating particle-antiparticle pairs right at their edge, one escaping, one falling in. That's EMCS at work near the event horizon.
Mind-bending stuff. Looking ahead then, the ultimate dream applications seem to be harnessing that 100% conversion of antimatter. Antimatter rockets.
That's the sci-fi holy grail, isn't it? Because the energy density is just so far beyond anything else. Forget chemical rockets, even fusion rockets would be dwarfed.
You could potentially travel the solar system incredibly quickly, maybe even reach nearby stars within a human lifetime.
That's the potential, yes. Various designs have been proposed using the annihilation energy to heat a propellant or using magnetic fields to direct charged particles from the annihilation.
But the challenges must be, well, astronomical.
Immense, and they tie right back to the equation. First, making antimatter. EMCS tells you that to make a gram of antimatter, you need to put in at least the energy equivalent of 2 grams of matter, one for the matter, one for the antimatter.
And our current particle accelerators are nowhere near efficient enough for that.
Not even close. We're talking efficiencies of maybe 1/1000% right now for converting electrical energy into antiprotons. The energy cost is staggering.
Okay, challenge 1.
Yeah.
Production. What else?
Storage. You have to keep antimatter completely isolated from normal matter otherwise.
Poof. Annihilation.
Right. So you need complex magnetic or electric traps kept at ultra-high vacuum near absolute zero. It's incredibly difficult engineering.
And if you manage to produce it and store it and then use it in an engine.
Then you have the radiation problem. Annihilation produces extremely high energy gamma rays. Shielding the crew and the spacecraft from that intense penetrating radiation is perhaps the biggest hurdle of all. We don't really have materials that can easily stop multi-MeV gamma rays without massive amounts of shielding.
So the very equation that promises ultimate energy also dictates the immense difficulty in actually using it safely.
It's a perfect illustration of the double-edged sword. The power is immense, but controlling it is a monumental task.
Okay, so let's try and wrap this up. We started with that observation about the huge c² and the tiny m for 1 joule.
And the first key takeaway is that the numbers themselves are mostly about us, about our chosen units.
The meter, the second, the kilogram, they make c look huge numerically, which makes them look tiny for a given e, but in natural units.
Where C1, it just becomes EM. Mass and energy are revealed as the same fundamental quantity. The conversion factor, c², is just bridging our incompatible human scales.
Second takeaway, that tiny mass for a joule isn't weakness, it's potency. It shows just how incredibly concentrated energy is when it takes the form of mass.
It's the universe's densest energy storage mechanism.
And finally, c itself isn't just some random speed. It's the fundamental constant linking space, time, energy, and mass. It's woven into the fabric of reality.
It dictates the rate of exchange between mass and energy and the speed limit for everything in the cosmos.
Which leads to a final thought, maybe. If mass and energy are truly just two faces of the same coin, this single entity, mass energy, how does that change the way you look at the world? That chair you're sitting on, the air you're breathing, it's all fundamentally just incredibly concentrated energy. And are there other big paradoxes out there in science that might just be waiting for us to find the right units, the right perspective, to see the underlying simplicity?
That's a great question to ponder. What illusions are created by the way we measure things? What deeper unity are we missing? mc² was perhaps the first great unveiling of such a unity. Makes you wonder what's next.